it turns out that transforming variables, this is things like taking a log of your variable or a square root of your variable, turns out to be useful for many things when we do linear regression. And you'd think, well, why would I ever want to take a log of my variable or a square root? That's just complicating life, right? But actually, it turns out that if you violated some of the assumptions of linear regression, these transform variables can be really, really useful because they can fix that violation. For example, if you've got a continuous outcome variable that's not normally distributed and you want to run a linear regression, what do? Well, one thing we talked about is if you had a continuous variable that's not normally distributed, you could use these alternative tests called the non-parametric tests, things like the Wilcoxon sum rank test, to analyze those data. But the Wilcoxon sum rank test is not a regression technique. So what if you want to actually run a linear regression on those data? As we talked about, that normality assumption is especially important when you're talking about kind of smaller, moderate sample sizes, especially of sample sizes under 100. Eventually, the central limit theorem kicks in and the normality assumption is less important. But for kind of small, moderate samples with a highly skewed outcome variable, you do have to worry about that normality assumption. And one way to get around this problem is there might be a transformation that you can take that very non-normally distributed outcome variable and transform it into something that looks more normal. So that's one use. I haven't told you too much about what to do in a linear regression if you have non-constant, that is non-homogeneous variances. So if the variance of your outcome differs at different levels of the predictor. I told you that's something you have to worry about, but I didn't really tell you what you can do to help with that if you violate that assumption. So if you've got a situation where you have really different variances, sometimes a transformation of one of your variables can fix that. Finally, for linear regression, you may often have the case where when you graph x against y, your dependent and independent variables, that you see that the scatter plot shows you that there is not a linear relationship. It's something curvilinear, some other kind of relationship. One way to deal with that potentially is to transform either the predictor or the outcome variable, and sometimes that will make the relationship more linear. So those are all possible uses of transformations. The most common transformations that you'll see, you might take a log of a variable. That's a very good one for normalizing things. You might see taking the square root of a variable, like if you've got a quadratic relationship, or the reciprocal of a variable. Those are probably the most common transformations. Just to illustrate, here I've got some right-skewed, highly right-skewed data. So I've got a data set. My outcome variable is something that's highly right-skewed. You're seeing in the histogram here. It's a pretty small data set, n equals 30. Let's say I want to analyze those data. I can't use t-test ANOVA linear regression on these data. The sample size is too small. The data are too non-normal here. Well, what can I do? Again, I could run some kind of non-parametric test on these data. But if I want to do a regression analysis, another option I have is to transform this particular variable. By transforming, all I mean is take the original values, and let's say in this case, let's take a log. So take all the original values and just take the log of those values. If I take a log of all those values and then plot those in a histogram, notice what happens. It's beautiful, right? It now looks so much more like a normal curve. This, what you see on the right-hand side, the log transform variable, it'll probably be fine to run that in a linear regression. Just to show you a couple of examples in the literature, this was a study that was looking at the outcome of inflammation, and they measured inflammation with something called CRP, C-reactive protein. But if you actually look at the graphics, you'll see what's on the y-axis is not CRP, it's log CRP. You can guess that the reason it's log CRP rather than the original CRP is that CRP is probably a highly right-skewed variable. Things like biomarkers are often highly right-skewed. If you take a log, it probably makes that variable much more normally distributed. The authors wanted to run a linear regression. They ran a linear regression here, so they used log CRP as the outcome variable. I like this figure. I wanted to just use this figure to point out two other points, a little bit of review from things we talked about this week and a little bit of a preview to what we're going to talk about next week. But this is an example of a categorical predictor that's been dummy coded. So just to show you that, what they did is for the predictor of drinking, they divided it into three categories: never drinker, infrequent drinker, and occasional or regular drinker. and then they dummy coded it for the purposes of running a linear regression. So they treated never drinker as the reference group, so that's treated as 0. They made a dummy coded variable for infrequent drinker. So this shows you, this first graphic shows you never drinker versus the infrequent drinker. And the second graph, they dummy coded the occasional regular drinker, so you see never drinker versus that group. So you end up with 2 regression lines, both compared to the reference of never drinker. And what this is showing you is that if you go from being a never drinker to an infrequent drinker, there does seem to be a drop in the log CRP levels. That is a negative slope there. And if you go from being a never drinker to an occasional or regular drinker, you also get this drop in the inflammation levels. I love studies that say that, you know, drinking is good for you. And so they were essentially saying, you know, if, there seems to be some drop in inflammation if you're drinking compared to not drinking. But that was dummy coded. That was represented here as a categorical variable. So just to review that concept. The other thing I want to point out that's interesting on this graphic is it also illustrates the concept of interaction, which is something I've alluded to, and we're going to talk about formally in the course next week. It's probably best illustrated in figure B here, so I'll just talk about figure B. So this was a study that was looking at people who were depressed. The dotted lines represent the depressed people here, and people who were not depressed, that's the solid line. And what you notice here is that the slope, the drop in inflammation, is much bigger for the people who are not depressed, and there's hardly any drop in inflammation for the people who are depressed. And that is an interaction. That's what we mean by an interaction. So this kind of picture nicely illustrates the concept of interaction. The slope, the relationship between drinking and inflammation, differs for different groups, for the depressed versus the non-depressed. That's an example of interaction, which again we'll talk about formally next week. One final real example from the literature. This was a study where the predictor and outcome variable are not exactly linearly related. So if you look, they were looking at body fat percentage as the predictor. Our outcome here is serum leptin levels. That's a protein in the blood. And you can see if you look at the scatter plot that it doesn't look quite linearly related, right? It's more of a curvilinear relationship. So what they did is that if just dropping a linear regression line on here wouldn't be quite right as a result, because it's not really a linear relationship, it's actually more curved. So they did a couple of different things. So one thing is they're showing you another graph here where they're graphing the body fat percentage against the log serum leptin. So again, the log is a really great transformation because you can see that makes that scatter plot look a lot more linear, maybe better fit by a line now. Not perfect, but still better than the original. So they actually tried 3 different things to deal with this non-linearity, and they listed them in the paper. So just to show you some of your options. So one thing that they did was they related the percentage of body fat with the log serum leptin concentration. That's what's represented by this little embedded graphic. They also tell you that they also looked at the log of percent body fat with the log of serum leptin concentration. So they transformed both the predictor and the outcome and ran that linear regression. And then finally, because it is kind of a curved, maybe suggesting a quadratic relationship, they also ran a third model where they did a quadratic. So they put into the model, this is worth writing out, they put in a beta for just percent body fat as itself, but then they also put in a beta for percent body fat squared. So you can also do this, is that you can say, well, the relationship between percent body fat and serum leptin is not just a linear relationship, but it's also quadratic, so you can put in a square of the predictor. So they also tried that, because you can see this looks like somewhat of a squared, a quadratic relationship. So all of those options are available to help make this more linear so that it's appropriate to run a linear regression.